I'm going to start putting the brakes on the breakthrough, or how I use simple logic to uncover a flaw in an old claimed theorem in statistical foundations. And these are the parts to it. I have to admit that I'm somewhat reluctant to present this for three main reasons. And one is that for sure, it differs from the presentations that we are typically giving in this forum on stat wars and their casualties, even though it most definitely has some serious casualties. For example, the topic, the likelihood principle, is incompatible, says Allan Birnbaum, with the main body of modern statistical theory and practice. Incompatible with Neyman-Pearson theory, confidence intervals, incompatible in general, even with such well-known concepts as standard error of an estimate and significance level. And Berger and Wolpert say the same. The trouble with the significance levels and why it's incompatible is that they involve averaging over sample points, other than just the observed point. The second reason I'm reluctant is that understanding the full arguments really requires more than could be given in a talk like this. I had promised to do it for a few groups, notably my 2019 summer seminar, and see if I could make it digestible. And in so doing, I'm foregoing some of the symbols that really are important, but that you could look at in the paper. And finally, it's something that I haven't been immersed in quite a while. And it's been 6 years plus a pandemic since I have been immersed in it. And so I may not be up on some of the fine points. But we can always continue in another forum, and there's always questions for you to pose to me. Okay, so I said there's these three parts to the talk, and then the imaginary dialogue. And the first part is an example one, very simple and well-known example that in fact Berger and Wolpert use to kick off their discussion in their book called The Likelihood Principle. Okay, this is a serious example of a conflict, they say. And this involves using a stopping rule to keep sampling until you're able to reject a null hypothesis at, let's say, a 0.05 level. It's a two-sided test of a null hypothesis that mu is 0 and is normal distribution testing. Keep sampling until you get, let's say, 2 standard deviations and then stop. So you try, let's say 10 trials, still don't get it, 20, 30, 40, and you keep going, and eventually, arbitrarily, let's suppose that they stop at 169. On the 169th trial, they have a statistically significant result. And so this is the stopping rule, and this is called optional stopping, and it's contrasted to fixed sample size, like if we started out with 169 trials to begin with. So I will use, let's see, I can point Y star here to represent the outcome in this optional stopping experiment, which will be E2, okay? Stopping with n equals 169. By contrast, X star will refer to the outcome in the fixed sample size experiment. That will be E1, and there it's fixed that we're going to do 169 samples. On the face of it, comparing these two outcomes, Y star and X star seem different evidentially. for a legitimate 0.05 assessment with the fixed sample size, you would get a p-value of 0.05. But with the optional stopping, the probability of erroneously rejecting the null hypothesis accumulates. And the probability of having reached by n equals 169, I wrote here 0.55, I think it's more like 0.4. I'm not sure where that number, I think came from David Cox, but whatever, we know that there's a difference. That's the key. Moreover, this is what's called a proper stopping rule. It will stop with finitely many trials, and it's assured of rejecting the null hypothesis, even if it's true. So we also have to assume that both of these experiments, optional stopping and fixed sample size, are seeking to make inferences about the same parameter, call it theta, the mean. And it also has to have the same value, even though we don't know what it is. Finally, the statistical model has to be given. That's a lot, okay? However, these two outcomes, X star and Y star, have proportional likelihoods. And the data itself can be seen as a string of 169 outcomes. But regardless of whether it came from E1 or E2, we have these proportional likelihoods differing just by a constant, okay? Generally like a coefficient on the outside. And often these are called the same likelihood when they have proportionality like this. Okay. Here comes the likelihood principle. It says, if the likelihoods from different experiments, E1 and E2, are proportional in this way, then inferences from the two should be the same. But because there's so many givens in this discussion, I adopt this shorthand. We start out with this notion of an LP pair, a likelihood principle pair, okay? Whenever X star and Y star from different experiments, E1 and E2, have these proportional likelihoods over the relevant parameter, I'll call them LP pairs. And the star, in fact, will indicate that they are LP pairs. And then we can talk in a general way about the inference that would follow or could be made depending on the account that you're in, based on experiment E and outcome Z. And in the paper, the 2014, I really like to put the experiment E as a subscript here that really points up the experiment more clearly, but this seemed easier to put on a slide. So here's the likelihood principle in its abbreviated form. It says, if X star and Y star are LP pairs, then the inference from X star should be equal to the inference from Y star. That's what it asserts. And of course, that's the focus, the controversial principle that I'll be talking about. And it's Allan Birnbaum that brings forward this argument in 1962. He was very keen to consider general principles of what he called informative inference, by which he meant really parametric inference within a model. And he was trying to generalize over different methods and schools, which is pretty impossible to do. So he had this notion of evidence, EV, that he might be able to generalize about. So this first example then is the optional stopping one, and the likelihood principle, this is Edwards, Lindman, and Savage, say that really when the rules or when the stopping rule finally stops should be irrelevant. The rules governing when data collection stops are irrelevant to data interpretation. And he's happy that with the likelihood principle, we restore the simplicity and freedom that's lost if you use Neyman Pearson tests or other. In fact, It's often called the stopping rule principle, which asserts the irrelevance of stopping. And so the book, The Likelihood Principle, begins with this example, as I said, and it's also the example you'll see in Edwards, Lindman, and Savage. And they say, suppose you collect data of any kind, not necessarily Bernoullian, nor identically distributed, nor independent, stopping only when the data thus far collected satisfy some criterion of a sort that is sure to be satisfied at some point, then the import of the sequence of n data actually observed will be exactly the same had you planned all along to take n, okay? Or this is Dennis Lindley. In calculating the posterior probability or inference about mu, the only contribution of the data is through the likelihood function. So if you have two pieces of data, X star and Y star with proportional likelihood functions, the inferences about mu from the two data sets should be the same. This is not usually true, he points out, in the orthodox frequentist theory, and its falsity in that theory is an example of that theory's incoherence. So we're emphasizing this disagreement here. On the other side, for sampling theorists, frequentist error statisticians, as I prefer, by contrast, this example, taken in the context of examining consistency with the null hypothesis theta is 0, is enough, says David Cox, to refute the strong likelihood principle. And my likelihood principle here is going to be the strong. I'll distinguish the weak in a minute. That's enough to even reject it. Because with probability 1, it's eventually going to stop with a nominally significant result, even though the null is true. And they all agree that you will eventually stop and erroneously rejecting the null hypothesis. The significance tester objects to this. The person holding the likelihood principle does not. To allow this also contradicts what Cox and Hinckley call the weak repeated sampling principle. And this principle is saying that a method that is wrong most of the time, if not always, should be rejected. Okay. So within sampling theory, we would make a distinction. We would not consider X star evidentially equivalent to Y star, right? We already said the p-values would be different. Whatever they are, they're going to differ. So what we have here can be called a violation of the likelihood principle, an LP violation. To put that in an abbreviated way, any case where you have X star and Y star, right? They have proportional likelihood. They form an LP pair. Nevertheless, the inference from X star is not equal to the inference from Y star, then you have an LP violation, okay? And this argument is supposed to hold for any form of inference, so long as it's one of these informative inferences about a parameter within a model, but it should hold for p-values, confidence levels, whatever. And I'm using the p-values just really to simplify the argument. Of course, someone could say they don't care about the error probability control and they don't care about weak repeated sampling, but I want to be clear, I'm not here trying to convince you of the error statistical account that violates the likelihood principle. Okay, what's of interest is that Birnbaum seemed to show that the frequentists couldn't consistently allow these LP violations, that they would have to give up something else. He himself, by the way, was a frequentist, so he was kind of alarmed and disturbed to see this. Okay. So he was trying, and he thought he had shown that this result holds for frequency-based statistical inference. And this is from a well-known paper by Evans, Fraser, and Monet, when they say, within the context of frequency-based statistical inference, Birnbaum argued that these two principles we'll talk about, conditionality and sufficiency, implies the likelihood principle. And it was considered a very exciting result of Birnbaum's. It was a breakthrough in statistics. It's in the breakthrough volume I mentioned. Savage says, without any intent to speak with exaggeration, it seems to me this is really a historic occasion. This is a landmark in statistics. Of course, I myself, like other Bayesians, have been convinced of the truth of the likelihood principle for a long time, and it follows very simply from inference by way of Bayes' theorem. But what was interesting about this, again, is that it seemed to hold for frequentists. And so it would be hard to point to even a handful of comparable events, says Savage. All of these traditional computations violated. And he also thinks that people aren't going to stop at the halfway house of using likelihoods. He says they're going to go full-blown Bayesian once they see the Birnbaum result, which was, remember, 1962. As I had said in my first paper on this, that I had no doubt that revealing the flaw in this alleged proof won't be greeted with anything like the same recognition, and it hasn't been. Okay, so we want to talk about sufficiency, which is really also the weak likelihood principle. And the thing is, if there were only one experiment, then outcomes with proportional likelihoods would be evidentially equivalent. So that's why this is called the weak likelihood principle. The thing about the likelihood principle is that it referred to two distinct experiments, okay? But if it's one experiment, then that holds no problem. You know, I gave you some supplementary materials, and one of the things in there is about sufficiency, and a familiar example of a sufficient statistic would be the number of successes in K trials, K Bernoulli trials, okay? If you were trying to make inferences about theta, the probability of success on each trial, K would be a sufficient statistic. And so anytime you had two identical values of K, you would reach the same inference with respect to theta. That's just ordinary sufficiency or weak likelihood. It's also assumed in this abbreviation here, whatever else you need for the computation in E. Okay. So that was the example one. Example two involves a mixture experiment. And it comes first from Cox 1958. Two measuring instruments of different precisions, or you shouldn't get blamed for something you didn't do or credit for something you didn't do. So here's how it goes. You flip a fair coin to decide whether to use a very precise or a very imprecise tool, E1 or E2. The experiment has two steps. First, you flip the coin to see whether you're going to perform E1 or E2. Then you perform it and you write down the outcome. What this conditionality principle says is that once it's known which experiment, which E sub I for I1 or 2, actually produced your outcome Z, then the p-value or other inferential assessment should be made conditioning on the experiment actually run. Now, it has to be required that the randomizer, in this case, the flipping, must be irrelevant to the parameter theta. Otherwise, this doesn't work. So I'll call it a theta irrelevant randomizer. And one of the examples that David Cox gave goes like this. In observing a normally distributed Z in testing that null hypothesis theta is 0, it might be that experiment E1 has a variance of 1, but the variance of E2 is great big, 10 to the 6th. Or it could be that they differ greatly in sample size to produce the same difference in precision. The bottom line is that the same measurement would correspond to a much smaller p-value if it came from E1 rather than E2 with its large variance. Okay. Now, it's possible that somebody would want to report, instead of conditioning on the experiment performed, they might want to report the precision of the experiment as the average of the two. This is called the unconditional assessment. And this is the convex combination of the two p-values averaged over the two experiments. And Cox identified this conditionality principle, which he's really calling the weak principle because there are stronger ones, to make this point. Suppose you know that you observed E2 with its large variance. And he says the unconditional test says we can assign it a higher, meaning smaller, level of significance than we ordinarily do, because if we were to repeat the experiment, we might sample some quite different distribution. But this fact seems irrelevant to the interpretation of an observation, which we know came from a distribution with the larger variance. And a little bit more of this at the upshot. The measurement using the imprecise tool shouldn't be getting credit because the measurer might have used a more precise tool. Nor should the precise guy be blamed because he could have used a less precise tool. So this seems obvious enough, yes? So CP, the conditionality principle, simply says, once it is known which experiment, E sub I, be it E1 or E2, once you know which one produced Z, you should condition on the experiment that actually produced the result. In other words, it's saying don't use the unconditional formulation where you average them together. It's important to keep in mind that this principle, conditionality, always requires that you know the experiment, which one was performed, and what the outcome was. If it's given just that, well, we observed something and it could have come from E1 or E2, and it doesn't tell you which one, then you can't apply conditionality. So if this seems kind of obvious that you should condition, then why was Cox's paper considered so important, an important criticism of certain frequentist methods that would use the convex combination? Well, as Allan Birnbaum himself notices, conditionality is not a mathematical principle. It's one thought to reflect our intuitions about evidence. There are contexts where the frequentist would report the unconditional assessment. For example, if there was going to be a lot of applications and you were really interested mostly in the average precision or something like that, and you could actually get better average properties, David Cox showed in some cases. So Cox admits, he says, if the object of the analysis is to make statements by a rule with certain specified long-run properties, the unconditional test is in order. If, however, our object is to say what we can learn from the data that we have, the unconditional test surely is no good. So the surprising upshot of the argument that we're considering today is It claims to show that if you do what seems sensible, conditioning on the randomizer, that you have to go all the way, so to speak, to conditioning on the data point, which would mean no error probabilities. And that's what Birnbaum's result purports. Okay, he purports that simplicity, sufficiency, and conditionality together entails the likelihood principle. And we wrote that it's not uncommon to see statistics tests argue that in frequentist theory, you're presented with this dilemma: either deny the appropriateness of conditioning on the precision of the tool chosen by a toss of a coin, or else embrace the strong likelihood principle, which means that frequentist sampling distributions are irrelevant, no error probabilities. We say this is a false dilemma and that it is an illusion, but it was up to me to show this, actually. And it's not so easy to dispel, thus my writing on this. So now we're up to the breakthrough. The shorthands, X star is going to refer to experiment E1, and the outcome X star, and Y star refers to experiment E2, and the outcome Y star. And to remind us, the likelihood principle asserts if X star and Y star are LP pairs, then the inferences from them should be the same, okay? Whenever X star and Y star form an LP pair, but the inferences are not the same, you have a violation of the likelihood principle, yes? An LP violation. And we saw an example in the example 1, where Y star came from optional stopping that happened to stop at n equals 169, as compared to X star with the sample size fixed at 169 all along. So this was an example. And of course, this just happens to be a dramatic example. There are many others, binomial, negative binomial, and really ordinary garden varieties. So we have an LP violation. Now here goes Birnbaum's argument. He will tell us about an experiment we can call a Birnbaum experiment. And it's a funny kind of mixture based on a likelihood principle pair. You observed Y star from experiment E2. It can be the optional stopping one again. Then you enlarge it to an imaginary mixture. You imagine it resulted from getting tails on the toss of a fair coin, where heads would have meant performing the fixed sample size experiment, with n fixed to 169 from the start. That's the first thing you do when you've observed Y star. The second thing you do is that you will report Y star as the same as X star. Here's how it's usually written. So you've observed Y star, but you will go ahead and report X star. X star will be reported if either you got Y star or you got X star. Either way, they're both reported the same. This was in cases of likelihood principle pairs. If you're not dealing with a likelihood principle pair, then just report it in the ordinary way. Okay, this is how it's typically put. And if you look at the supplementary materials I put, you can see it's always stated this way by everybody who considers this. And the Birnbaum argument focuses on the first case because, of course, that's the interesting one, where we have an LP pair. And we're going to see whether we're forced into the likelihood principle or not. Now, within this Birnbaum experiment, so we have just defined this statistic, we can call it TB, to go along with EB, the Birnbaum experiment. It's a sufficient statistic within this experiment that I'm calling a Birnbaum or Birnbaumized experiment. Okay, so how do you make an inference within a Birnbaum experiment, EB? Well, what you would do is report the convex combination if you were doing p-values, okay? And you get the average, whatever it is, 0.3. Because what happened is you have just identified Y star and X star. Now I said it was a funny kind of mixture. That's for two reasons. First of all, it didn't happen. It's given here that you only observed Y star from E2 optional stopping. Nevertheless, you're to report an outcome as X star from E1, even though you actually observed Y star from E2. And the other thing is that the inference is going to be based on the unconditional mixture. And we can abbreviate it as Birnbaumizing. And we're supposed to do this for every LP pair, because you have to remember that the likelihood principle is a universal generalization that says for any pairs, give me any Y star, I'll show you that if it has a pair in X star, then you ought to treat them the same inferentially, unless you want to violate conditionality or sufficiency. Now, within the Birnbaum experiment, it does appear you must treat X star as evidentially equivalent to its likelihood principle pair Y star. After all, they are reported in exactly the same way. So now we get the first premise of his argument. If you did use this Birnbaumization, inference within EB, indeed, X star and Y star are evidentially equivalent. They're both equal to this unconditional, the convex combination. The second premise is, well, if you use conditionality, then the inference from Y star is actually P2. This will be the p-value that goes along with the optional stopping, 0.5, whatever it is. And the next part of that premise, if you observed X star, then you report the ordinary p-value, 0.05. Now, the conclusion is supposed to be, therefore, P1 must be equal to P2, that you must draw the same inference from X star and Y star. But we are starting with an LP violation. We know with the optional stopping versus the fixed sample size that the p-values differ. So we have true premises and a false conclusion in any case of an LP violation. So this argument is not valid. That would be the definition, in fact, of an invalid argument. We can formulate Birnbaum's argument as a valid argument, but then it won't be sound. It will turn out that the premises must, at least some of them, be false and even conflicting with each other. Okay. But instead of continuing with the formal paper, what I'm going to do is sketch an exchange, that an imaginary exchange, like an imaginary mixture, with Allan Birnbaum. And I post it each year. I vary it every year on New Year's Eve. It's like that movie, Midnight in Paris, but Midnight with Birnbaum, where I meet up with him. And we talk, in fact, about this result. And these are just the main parts. So the error statistical philosopher, I say, it's great to meet you, Allan. I've always wanted to meet you, and I happen to be writing on your famous result, the likelihood principle. And Birnbaum says, ultimately, you know, I rejected the LP as failing to control error probabilities, except in the trivial case of testing point against point hypothesis, where they're pre-designated. I'd say, I suspected you found the flaw in your argument at some point, because it doesn't seem to work. Birnbaum, well, I'll happily invite you to take any case that violates the likelihood principle and allow me to demonstrate that the frequentist is then led to inconsistency with either sufficiency or conditionality. And whoever wins this little argument, he says, has to pay for the whole bottle of vintage champagne. Oh, I'll be happy to pay for it, I say. Good, you'll have to, Birnbaum says. Now take any violation. Let's suppose we're doing two-sided normal testing. Y star from optional stopping E2, and it stops with a 2 standard deviation difference. It happens to stop, let's say, at n equals 169. I will show you that Y star must be inferentially equivalent to X star from the corresponding fixed sample size experiment E1, where n was fixed all along to be 169. So I will show you the two inferences have to be the same. And of course, both of them are making an inference about the same parameter, and the model is given and all of that. Do you agree, he asked me, that for a frequentist, Y star is not evidentially equivalent to X star? Yes, that's a clear case where we reject the likelihood principle, and it makes perfect sense to distinguish them, to distinguish their p-values, because optional stopping makes the p-value quite a bit higher. I don't see how you can make them equal. Birnbaum says, well, I'll show you then. You'll have to renounce another principle that I believe you hold, conditionality. I assume you hold sufficiency. He doesn't really make much of it. And I just laugh. Okay, so he says, suppose you've observed Y star from E2. You admit, don't you, that this outcome could have occurred as a result of a different experiment. It could have been a fair coin was flipped, and it was agreed that if you get heads, you perform E1, fixed sample size, and tail instructs you to perform the optional stopping test, E2. And it happens that you got tails, and furthermore, you run the experiment, and you manage to stop at n equals 169. This is a mixture experiment. I say, well, that's not how I got Y star. Okay, I know I got it from E2, but okay, it could have occurred that way. Good, he says. You must grant further that your result could have come from a special variation on this mixture of mine. Call it a Birnbaum experiment, EB. You see, in EB, if the outcome from an experiment that you actually performed has an outcome with a proportional likelihood to one in some other experiment not performed, let's say E1, we say your result has an LP pair. He's using our abbreviation. In that case, EB stipulates you're to report Y star as if you've determined whether to run E1 or E2 by flipping a fair coin, and we assume it's theta irrelevant. So let's see if I understand a Birnbaum experiment. I run E2, and when I stop, I report my observed 2 standard deviation difference came from E1, even though I know it came from E2. And as a result of this strange kind of mixture. Yes, Birnbaum says, or equivalently, you could just report Y star was my result, and it could have come from either E1, fixed sampling, or E2, optional stopping that just happens to stop at 169. And the proof is often put this way, it doesn't make a difference. So you're saying if my result has an LP pair and experiment not performed, I should act as if I accept the likelihood principle. And so if the likelihoods are proportional, then the outcomes lead to the same inference? Well, wait a minute, he says. Experiment EB is an imagined mixture. It's a single experiment. So you really only need to apply sufficiency, which everyone accepts. You don't have to apply the likelihood principle, which refers to 2 experiments. Okay, the ES philosopher says, so Birnbaumization has turned the 2 experiments into 1. But then how do I calculate the p-value within the Birnbaumized experiment? He's taken aback by my use of the word Birnbaumized. I don't think anyone's ever called it that. He said, well, I just wanted to give it a shorthand. So anyway, how do I calculate the p-value? Well, you would report, he says, the overall unconditional p-value, which would be the average over the sampling distributions, the convex combination, right? Okay, so you're saying, if I observe a 2 standard deviation difference from E2, I don't report its p-value, 0.55, whatever it is. Instead, I'm to report the average p-value, averaging over some other experiment, E1, that could have given rise to an outcome with a proportional likelihood to the one I observed, even though I didn't obtain it this way. I'm saying, he says, you have to grant Y star from an optional stopping experiment E2 could have been generated through a Birnbaum experiment EB. And if you follow the rules of EB, Y star is evidentially equivalent to X star. That was the first premise of my argument. It goes like this. Within EB, the inference from Y star is equal to convex combination, okay? And so the 2 will be treated the same. I say, well, that's just a matter of how you defined the inference within your Birnbaumized experiment. We still have P1 is different from P2. 0.05 is not the same as 0.55. So I don't see the contradiction with my rejecting the likelihood principle. Hold on, Birnbaum says, I'm about to get to the second premise. That was just premise 1. Oh, boy, what's premise 2? Premise 2 is this, Birnbaum says, surely you agree, following conditionality, that once you know from which experiment the observed 2 standard deviation difference actually came, you ought to report the p-value corresponding to that experiment. You ought not to report that average convex combination as you were instructed to do within EB. And this gives the second premise that the inference from conditionality, the inference from Y star is just P2 by itself, no averaging. So having first insisted I imagine myself in a Birnbaumized experiment and reporting the average p-value, I'm now to return to my senses and condition to get back to where I was before I enlarged the experiment. Birnbaum says, yes, at least if you hold to the conditionality principle, and I'm sure you do, because I know you were working with Cox on this. Okay. And likewise, you would do the same thing. If you knew it came from E1, the p-value would be 0.05. There you go. You've got the result, he says. Well, the thing is, conditionality is defined for mixtures where you flip a coin to determine if E1 or E2 is performed. You can't perform the following. Toss a fair coin. If it lands heads, perform an experiment E1 that yields a member of an LP pair X star. And if tails, observe E2 that yields Y star. We can actually do that. We don't know what would have resulted from the unperformed experiment, much less that it would have formed an LP pair with the outcome I actually observed, Y star. There's just this single experiment, and I got Y star, according to the givens here. And CP stipulates we know which one was performed and what its outcome was. Birnbaum says, wasn't I clear that I'm dealing with hypothetical or mathematical mixtures? I'm not dealing with actual mixtures. Just need to put this plug in. I realize that a lot of people, including brilliant statisticians, have rejected my argument or tried to block it because it deals in these mathematical mixtures. And I say, I want to give your argument maximum mileage, and I'm prepared to allow conditionality to be defined for hypothetical theta irrelevant mixtures. And here's how I picture these hypothetical mixtures. We can envision the mathematical universe of LP pairs out there, right? Each is imagined to have been generated from a theta irrelevant mixture. And when we observe Y star, we pluck the X star companion that we need for the argument. But they're kind of all out there, and they actually could have been run one of these days. You know, eventually you would get that matchup and you'd get LP pairs. So imagine they're out there. Of course, if an outcome doesn't have an LP pair in some other experiment, we just proceed as normal. That's fine. Your task is still to show that if X star and Y star are LP pairs, the inferences from the two should be the same. That's the LP. Exactly, he says. You pluck down, you've got Y star, you pluck down X star, you get the first premise, get the second premise, you get the LP. Well, clever, but proof is unsound. Either it's going to be invalid or valid in form, but with false premises. Here's one rendition of it, and it comes out invalid. First premise, if you use Birnbaumization, TB is sufficient, then yes, the inference from X star equals the inference from Y star, and they're both the convex combination. And now you have two applications of conditionality, that the inference from Y star is P2, the inference from X star is P1. The conclusion is supposed to be P1 equals P2, but we have an LP violation here. So the conclusion is false. The premises are true, the conclusion is false, and that's the definition of an invalid argument. So you can't induce that conclusion. You could see the argument as formally valid, but then the premises conflict. Here's how that can happen. You will put EB all the way through, so it's formally valid. Here it says in EB, the inference is the convex combination. And from CP, you will condition twice. Okay, the trouble is these two conflict with each other, but they're if-then statements. So they actually, you know, can hold true. But because the premises contradict each other, the argument is not sound. It's invalid, but unsound. If the first premise is true, then 2A and 2B are false. I mean, you have to make up your mind about how the inference directive is going to go, conditional or unconditional. If you keep to this valid formulation, the premises could hold true, but only in special case where there's no LP violation. With LP violations, we actually have three different distributions, E1, E2, and EB. Otherwise, the premises contradict each other. Of course, anything follows from a contradiction, and the argument may be playing on that fact. Alternatively, I can get the premises to come out true, but then the conclusion is false for any LP violation. Again, invalidity. And any LP violation will be a case where the argument is unsound. The only thing would be to restrict it to cases that couldn't have any LP violations. And he says, well, of course, I'm really not interested in showing the LP follows for these other accounts for Bayesians and likelihoods. They have much simpler ways to derive the LP follows directly from Bayes' theorem or from inference by way of likelihoods. My argument was to hold for approaches which are independent of this Bayes principle. Well, the trouble is, I say there's no contradiction for a frequentist by dint of holding sufficiency and conditionality and still having LP violations. A little aside here that contemporary non-subjective Bayesians do concede that they have to live with some violations of the likelihood and stopping rule principles. So Birnbaum says, well, some people still think it's a breakthrough. And this is just the last point here. I've come to see that really clarifying the entire argument turns on defining conditionality. Yes, Birnbaum says, the monster of the likelihood principle arises from viewing it as an equivalence instead of going in one direction, which is the way it always had been, going from mixtures to the known result. And I say in my 2014 paper, I also view it as an equivalence, but there's a subtle equivocation that invalidates the move to the likelihood principle. I have a few ways to try to make this out. This is one of the reasons the example is so interesting, especially for philosophers, because there's this logical mood. Okay, given y star is known to have come from E2, it's true, it doesn't matter if it was the result of an irrelevant randomizer to choose between E1 and E2 or fixed all along. That's because once I know it came from E2, I have all I need to compute the inference. I know the sampling distribution. If you tell me things like it could have been this, it could have been that, I could have taken the train, whatever, it doesn't change the inference. So we can have that equivalent there. It's completely equivalent to conjoining an irrelevancy. But it doesn't follow that given y star is known to have come from E2, I don't have to know whether it came from E2 or E1. And I think there's this little equivocation here that makes it seem that because it's irrelevant if I report it, it could have come in this other way, that therefore I really don't need to know if it came from E1 or E2. But the only reason that this equivalence holds is that I know it came from E2. So I suggest you can see it as an equivalence, all right. The only mistake is in supposing that conditionality is this equivalence, that inference from the Birnbaum experiment is the same as inference from the individual experiment. That would obviously be wrong. One is the convex combination, and one is just the individual. So some people like to draw this picture, but the trouble is you don't get the same EB in the corners. It's like a fallacy of four terms. I'm going to stop there.